First subsystem we're going to look at is an example of a subsystem for a shooter. Um, all of these subsystems, which we'll take a look at, are really for example purposes only. None of them would work with um, any robot that 3061 has had or any robot that other teams might have had. They're really here to show best practices and make things a little bit more concrete in terms of how to implement subsystems within 3061 lib. All of these follow the AdvantageKit architecture, and so we'll see that throughout. Um, as we look at each of these, we'll focus on some other related topics as well, um, whether that's things like sysid, which we'll save for a later subsystem, or fault reporter, which we'll look at in the subsystem, or some other advanced like CTRE features and things like that. So we're going to start with this one. This is for a shooter. The shooter is modeled to have independently controlled top and bottom wheels. This is modeled after the subsystem 3061 used in 2024 for Crescendo, where we had top and bottom rollers when shooting notes. So here are some highlights here. Some of these we'll focus on, some of these we won't. So an interpolating double tree map to map distances to velocities. We'll talk about that. That's a really handy technique. We'll see how we can use debouncers to know when we're at a set point and staying there. We've seen tunables before, but we'll look at tunables again. We'll see that each of these subsystems use a simulation class to help us model the behavior of the subsystem when running in simulation. We're not going to focus on sysid at this moment. We'll save that for when we look at a different subsystem, the ARM. But we will look at system check and fault reporter stuff as well. So unlike the vision subsystem, which we looked at earlier, and the swerve drivetrain subsystem, which we looked at earlier, the shooter subsystem is a much more traditional AdvantageKit subsystem. So it extends subsystem base, just like all subsystems do, maintains a reference to its IO object. Shooter IO is the is where our hardware abstraction layer is, and so sub or classes that implement the shooter IO interface, like shooter IO Talon FX, is what would actually be created. Here's the shooter IO inputs, which we will use inside of periodic. Things that are tunable. So generally, we have found it helpful to have a tunable for testing mode. We like to use testing mode um, when we're first bringing a mechanism up. Often we can do that just within Phoenix Tuner without having to run our code at all. However, there are limitations to Phoenix Tuner. So for example, for the shooter, there are top bottoms and top motor and a bottom motor. We want to control both of those. And so we can't do that through Phoenix Tuner. So we use testing mode and do that instead. When in addition to having testing mode is a tunable, so we can turn it on and off, we then have several other tunables that we can use when we are in testing mode. So we have top wheel and bottom wheel current, so we can directly set the current for the top and bottom wheel. And then we have top wheel and bottom wheel velocity in rotations per second. So we can actually command a specific velocity for the top and bottom wheel. This is useful for sure when bringing the mechanism first up, but it's also useful for characterizing the system in terms of, again, this is modeled after the shooter mechanism in Crescendo. We could put the robot at a certain position on the field, tune the velocities of the top and bottom wheel until the note shot was very accurate, capture that, move the robot somewhere else, determine the appropriate top and bottom velocities, move the robot somewhere else, and so on and so forth. So it's very efficiently allowed us to characterize the mechanism and determine appropriate velocities for different locations on the field, for example. And that connects to this next part here too, which is the shooting map. It's an interpolating double tree map. And so what this allows us to do is to create a map from distances to velocities. And so we can collect as much data as we want on the field. In this example, we simply have 3 different distances and 3 corresponding velocities. The interpolating tree map will do a linear interpolation between, when you provide a distance, it will interpolate between the 2 points that it has and then determine the appropriate velocity as well. Like I said, we're not going to talk about sysid right now, so I'm going to skip over that. We'll look at that when we look at a different subsystem. When we construct our shooter object, is provided a reference to the specific IO the hardware specific IO object, which it saves, populates the shooting map. This simply goes through those arrays we saw up above and populates the tree map. We do have this field measurement offset. So one thing that we had found in the past is sometimes there's a slight difference between our practice field and a given competition field, or one competition field and another competition field. So during field calibration, we don't have the opportunity to like dial in the shooter and actually shoot things. We can't have the robot enabled, obviously, during field calibration, but we can make some measurements um, and determine that, oh, things are a little bit different. Let's have a slight offset here, either positive or negative, to map between this competition field and our field at home so that the velocities work out. So that's how we account for that. All right, I said we talked some about fault reporter. Register system check is a method we call in the singleton, and we provide it a reference to a system check command. Let's look at what that is. So we're going to jump down here to get system check command. This returns a reference to a command, and this is how we determine that the shooter in this case is working as expected. Generally, there's going to be a sequence of commands within a command. And we're going to go through all of them. In this case, we're checking several different distances, and that the velocity is as expected. The way we construct this is we have our command sequence of all the things we want to test, and then we use the dot until decorator. Say keep doing the sequence either until it finishes or until there's a fault. Once there's a fault, we might as well stop the test. We don't want to keep going. And then another decorator, stop the shooter. We don't want to leave it running. So this usually our get system check command method, and we'll see this in the other subsystems too. It has some sort of a helper method like get preset check command, which has itself another sequence where it sets the velocity, waits a couple of seconds, which should be plenty of time for it to get to the set point, and then it calls this check velocity method to see that the wheels are turning at the right speed. So the check velocity helper method, here's what the top and bottom velocities should be. And so it checks if it's within tolerance. And if it's not, it adds a fault through the fault reporter. It's like, hey, the bottom shooter wheel velocity is too low. It should be this, but it's that. Or it's too high. We check it for the top as well. This is great because even if you have like your in-pit system check routine in your checklist, and this does not eliminate the need for that. That is still something that we certainly have. But this can check things that we can't necessarily accurately check with the human eye. So let's say there is a bearing that's about to fail, or something else is wrong with the mechanism and it can't reach the speed. It may look just fine and sound just fine when we run our system check, but this code would detect like, no, it's slow. Like it should have reached the speed and it's not. So it helps us out with that more robust system tests in the pit. All right, so that's our check command. So that's it for the subsystem class. Not too bad. Oh wait, got way ahead of myself. That's it for the constructor. All right, let's look at the periodic method. Periodic method. First thing we always do in a periodic method of a subsystem is to call the update inputs method on the IO object and pass along the inputs like we do here. The next thing we always do in a subsystem is to invoke the process inputs object on the logger for AdvantageKit to log that inputs object as well. Then we do whatever needs to be done periodically. For most subsystems, it's nothing, right? Because everything that the subsystem does is going to be invoked through a command of some sort. It's not going to necessarily do anything inside of periodic. We have specific code here, though, for if we're in testing mode. So all of this is only if we're within testing mode. So if we are within testing mode, Then we're going to look at the tunables, and if they're not 0, we're going to set like a velocity or a current on either the top or bottom wheels. We prioritize velocity here, but if you want current, just make sure velocity is 0 and change the current. One thing to keep in mind is if you try to stop it by setting it back to 0, it won't actually stop, because if it's 0, it's ignored. So we set it to like 0.01 and it still stops. So this is all just for testing. Okay. Um, and none of this code will run like at a competition, because tunables won't be tunables. They'll just be constants, and it'll be set to 0 for testing mode. All right, then we always do this log tracer record at the end of every periodic method to determine how much time did we spend inside of the shooter periodic method for profiling. All right, other interesting methods that we have here. We have a set idle velocity here. You may want your shooter's idle, if you have a nice transition where your shooter doesn't have to be stopped when a game piece is fed, you might want a non-zero idle velocity, so you're not drawing too much current, but yet you don't have to have that initial current hit of getting the wheels started. So you could have an idle velocity here. We have a set velocity method that takes in a distance. We log that, and then we use our map to determine what the velocity should be corresponding to that distance. We have methods here to determine if we're at the set point. We don't want to shoot until both the top and bottom wheels are at the set point, nor do we want to wait any longer than we have to, because that just wastes time. So we use a debouncer here for that. So basically, we don't want to simply check that the current velocity is within the tolerance. We want to make sure it stays within the tolerance for a certain period of time. And this is something you can tune based on your mechanism in your game and your priorities and things like that. Because if you simply check if it's within the tolerance, let's say your mechanism isn't well tuned, you might happen as you're just flying by your set point to be within tolerance one instant, and the next you're going way too fast or too slow, or whatever it happens to be. So we use a debouncer, and we set a period of 1/10 of a second. So 1/10 of a second is 5 cycles of periodic. So we want to make sure that we stay at the set point for 1/10 of a second before we say, yes, we're at the set point. If that's too much time, maybe the system is tuned really well and it's not needed, you could reduce that period. Maybe for sometimes it needs to be greater. This is just an example of using a debouncer to determine that we're at a set point. Of course, it would need to be tuned for a real mechanism in a real game. That's it for the subsystem class. Let's look at the other interesting things. Every subsystem has a constants file. We always have a subsystem name constant so that we log everything consistently. This is where we have our CAN IDs for our top and bottom motors. Here's our PID values for the top and bottom motors. Here is our feed forward constants that we got from running sysID. Again, we'll talk more about sysID in the context of another subsystem. Our current limits for the motors. And what else do we have here? The gear ratio, whether things are inverted, idle velocity, velocity tolerance for the system test, things like that. So those are all the constants. Our shooter IO interface defines the shooter IOInputs class. This is all the stuff that will be logged inside of at the top of periodic. So we log same things for the top and the bottom motor. We want to know whether it's connected. We want the stator and supply current. We want its current velocity. We want its reference velocity. That is from a closed loop perspective. Where is it told to go? Closed loop reference velocity, rotations per second. You're like, wait, these are the same thing. Yes, they are, and we'll see how they differ slightly. Well, not how they differ slightly, how we log them slightly differently. What is the closed loop error? Temperature of the motor, voltage applied to the motor. Update inputs, of course, will be always one of the methods in our IO class. And then these are the specific methods. Again, these are all things to command something, never accessors. All that would come through update inputs, but we want to set the top or bottom velocity or the top and bottom current. We only have one class that implements the shooter IO, which is the shooter IO Talon FX. We don't need to have one for simulation because CTRE supports simulation itself. We just add in a little bit extra, as we're going to see in a moment here, to model our system. But if we had a shooter with a different type of motor or something, we'd have a different class as well. All right, so here's our shooter IO Talon FX, implements the shooter IO. In general, we create instance variables for all of the requests we're going to make through Phoenix 6. So we're doing a velocity request for the top and the bottom motor. So we have two velocity torque current FOC objects there. We create instance variables for all of the status signals, the things that we want to read from the devices. So we have that for the top and bottom motor, and we have both the currents, the angular velocity, the temperature, the voltage. You'll notice we don't have the closed loop ones there. I'll comment on that in a moment. We keep track of the reference velocity for the top and bottom motor, and then whether it's connected or not. We also have this velocity system sim object here for the top and bottom motor. And when we configure that, we'll talk a little bit about that as well. We have an alert object here, which we will trigger if we can't configure the devices. And then we have things we may want to tune. So this is the PID and the feed forward static for the top and bottom motors. And then the actual references to the corresponding Talon FX objects. So in the constructor, for our hardware specific class here, we construct each of the devices, the Talon FX objects, based on the constants and the CAN bus name that we get from the robot config object. Usually this would be on a carnivore, for example, so we'd have a CAN bus name that's something other than an empty string. We construct our request objects for velocity, torque, current, FOC for the top and bottom motor. We get references to all the status signals we want. And then here's something we do for performance. We register all of these signals with Phoenix 6 utility. And the reason why we do this is to improve performance. So every subsystem will register all of its signals with Phoenix 6 utility. If we look at how that is done, we keep a list for the carnivore and a different list for what would be on the RoboRio CAN bus. And then there's a method here called refresh all, and it will basically refresh all the signals at once. And that's just more efficient with Phoenix 6 than to refresh status signals one by one, or even to refresh a group of them for an entire subsystem. He will refresh all of the status signals for all of the subsystems all at the same time. And I think this came up before, but we do call refresh all inside of the robot class at the start of robot periodic. So we refresh all the status signals here. And then we can just use those status signal objects before, and we don't need to refresh them, which is great. So we have to register them, which is done here. We then have a method here to help us configure the top and the bottom motors. The configuration is nearly identical. We just need to pass in a flag whether it's the top or bottom one because it's slightly different. So let's look at that. We make a Talon FX configuration object. We might have different current limits for the top versus the bottom motor and different PID values for the top versus the bottom motor. So we deal with that. We specify the sensor to mechanism ratio based on the gearing we have, whether it's inverted. We want it in coast mode because we're doing velocity, torque, current, FOC control. We don't want it slowing down. And then here we use the Phoenix 6 util class as well to apply and check the configuration. So what this utility class does is we pass in a reference to the device, the config object, and the alert that we created up above. It will attempt by default 5 times to apply the configuration, and then it will actually read that configuration back. Ensuring that the configuration makes it to the device is is critical. Um, if it doesn't, like that would be a huge problem. Imagine like the motor's inverted, but like that didn't make it in the config, and then your thing's going the wrong direction, right? Like end of match type of things. So we want to make sure everything has been applied. If it fails 5 times, that would be really, really bad. An alert will pop up. We can like power cycle the robot and hope that fixes whatever's going on. Maybe it's indicative of a device that's failing. I don't know. But we definitely want to know if that's the case. So we use this, every subsystem uses this apply and check configuration method to ensure that the configuration makes it to the devices. For every device, we also use the fault reporter to register the given hardware. So we register whether it's the top or bottom motor, pass in a reference to that motor. This will periodically do some checks when the robot is disabled to see if there's any faults on that device. And we'll look more at fault reporter later. But it's important that every device gets registered with fault reporter in the IO specific class. All right. So we've configured everything. We then have some simulation stuff to do that I referred to earlier. We create a velocity system sim object for each of the top and bottom motors. This helps us simulate the system. So CTRE has simulation built in, but it doesn't have like a physics model of the actual like shooter design. And so this velocity system sim class takes care of that for us. We need to give it a reference to the Talon FX device. We need to specify what the KV and KA is from characterizing the shooter. That's how it can model the physics of it, whether it's inverted or not, and what the gear ratio is. And so 3061 lib has a collection of these, a collection of different simulation objects. So we have one for simulating an arm system, an elevator system, and this is the velocity system sim. So we look at this. This is the object we're creating in this case. And basically for anything that's like a shooter or a velocity system, an intake, a roller, things like that, we can use this object. The physics characterization really comes from those parameters here. But what this allows us to do is to get the sim state from CTRE, which is all supported. Specify the orientation, but then we create in this case, a linear system simulation using the WPI lib class to do this, to model the physics of it. You'll see later in a moment, we always call update sim at the end of periodic, but if we're not in sim, it just returns because we want to be efficient. But if it is in simulation, it's very important that we call set supply voltage on the simulation object from CTRE. And then we get the motor voltage from CTRE's simulation state object, and then we pass that to our linear system simulation, and say, hey, here's the input to this modeled system in terms of the voltage. We update the model based on our loop cycle time, and then using our linear system simulation model, we can get the output of this, which will be how many radians per second things are turning. We do the math to turn it into rotations per second for the motor, and then rotations total for the motor. And then we add that back into CTRE's simulation object. So CTRE supports simulation. We just have to have some extra code here to provide basically the physics model to go with it, which we do by leveraging WPI lib's linear system class. Rather than putting like all of this type of code in subsystems over and over again, these 3 classes cover basically all the cases we run into. And so it's a lot easier to simply create one of these objects when we construct the object, and then we'll see in update inputs, we just call update sim and everything is done without making this class any longer or more complicated. So that's how we handle all the simulation type things. All right, update inputs. So update inputs has a parameter, which is the shooter IO inputs. For connected, we use a debouncer for connected. If a signal, so we determine if the motor is connected if the signals are all good. If the signal isn't good for a very brief period of time, things are probably okay. Um, so we only really consider a motor is no longer connected is if we don't get any signals from it for half a second. Okay. Um, really should be much less than that, but like that's our threshold. So if we get nothing for half a second from a motor, we're gonna say that motor is no longer connected. Um, and then we know we have a problem. Here's where we update all of the other things. For the top motor and the bottom motor, the only input properties we haven't updated is the closed loop reference velocity and the closed loop error velocity. We only update those when we're in tuning mode. The reason for that is their performance. We take a little bit of a performance hit. um, because we can't have these status signals in advance necessarily. We actually get the status signal from the motor and get the value right here, which it takes a little bit longer. And the reason why we do that here is because when you call get closed loop reference on your motor, the status signal that returns depends on your current control mode. Um, and so if the current control mode isn't like velocity, um, torque current FOC, then we're not going to get the right status signal object. And sometimes we have subsystems where our control modes change and vary. We might be doing current at one point and voltage another, and velocity at some point. I don't know. And so we we have to get it on the fly. Um, Really, this is most helpful when we're tuning the system. Um, And once the system is tuned, we don't really care what the closed loop error and the closed loop reference is. We already have what the commanded reference was, which should match this one anyway. So we only do this when we're in tuning mode to make things run a little faster. Um, all of this, again, we're using the if change method here on our tunables to say if, hey, if the PID or KS for our shooter top motor has changed, update things appropriately. If the PID or KS for the bottom motor has changed, update things appropriately. You'll notice we're just applying the configuration here. We're not confirming that it's been updated properly. This is only going to be done when we're tuning. So this isn't like competition critical. It'll be okay. Here's where we update the simulation like we talked about earlier. The rest of these methods are the methods that we have to implement as part of the IO interface. Um, they're really pretty easy to they just redirect to some sort of set control method on one or more motors. So here's how we set the velocity for the top motor, for the bottom motor. You'll notice here is where we're caching the commanded velocity. Again, this is done for performance reasons, as I explained previously. There should be a couple for current. Did I skip over the current ones? Ooh, I need to implement that. I'll go back and add those. We don't have this set shooter wheel top current, bottom current, which needs to be added. All right. So that's an example of a subsystem, and specifically a subsystem that would model a mechanism that we're controlling its velocity, and shows off a lot of the best practices related to that.